Now let us come to the calculation for harmonic oscillator. So path integral for harmonic oscillator. Here S of x, the real time action, is given by integral dt ti to tf x dot square minus omega square x square. X of ti is xi, x at tf is xf. The strategy is that write x of t as x lower bar of t plus y of t, where x lower bar is a classical solution, is the classical solution, is the classical solution corresponding to these initial and final conditions, which means that x lower bar ti is equal to xi and x lower bar tf is equal to xf. And that in turn means y ti is equal to y tf is equal to 0, as I have mentioned earlier. And also, this is a fixed path. This is a fixed path. Therefore, d of x is same as d of y. Now, then you could calculate, therefore, s of x, which is s of x lower bar plus y. So you can, in general, you should view it as a Taylor expansion of the action around the classical solution. But for harmonic oscillator being a quadratic function, the Taylor expansion ends at the quadratic level. And since x bar is the classical solution, which is that first order variation is 0, there is no linear in y term. So this is given by s of x lower bar plus half m ti to tf dt y minus del t square minus omega square y. Therefore, that the kernel of the propagator is given by, if you substitute this in the path integral expression, then this is a fixed phase that will come out. So e to the power I by h bar s of x lower bar. Then within the path integral, you will have dy exponential I over h bar times m by 2 integral dt ti to tf y minus del t square minus omega square y. This is a classical phase. This is a classical contribution, which is a phase. We will carry it as phi cl. And then in the Euclidean, then the path integral part, we will go to the Euclidean description. basically our job now is to do this calculation of the path integral, and that can be done by so path integral is integration over the paths, but the paths can be parameterized by performing Fourier transforms, and the Fourier coefficients can be the parameters of the infinite number of parameters that parameterize the paths. Actually, if you think of that curly F space, the space of paths, then the Fourier coefficients can be viewed as the coordinates in that space, and Fourier basis can be viewed as the basis, coordinate basis in that space. So we will do the same thing here. So here y bar as a function of u, this is ui and this is uf. We have all sorts of paths which will whose boundary conditions they vanish at ui and uf. So so if you do Fourier transform, then you can write u bar of u, y bar of u to be equal to sum over n greater than or equal to 1 Sn u y tilde n, where Sn of u, these Fourier modes are proportional to sine n pi u minus ui divided by uf minus ui. And the normalization is fixed by the condition that du ui to uf Sn u is equal to Kronecker delta. Then you can show, you can calculate that del u square of Sn of u is equal to minus lambda n Sn of u, where lambda n is given by n square pi square. You're just taking the double derivative of sine, so not uf minus ui whole square. Now, using this result in here, where you have this integral, then the integral, each y bar factor can be given this summation here, right? And then this operator will give you certain eigenvalues. And when you have these two Sns and then u integral, it will come, it will be a double sum with a Kronecker delta. Therefore, after absorbing the Kronecker delta, you'll be left with a single sum. So if you do this calculation which I just described, then you can show that du ui to uf y bar minus del u square plus omega square y bar is equal to sum over n greater than or equal to 1 lambda n plus omega square y tilde n y tilde n. And therefore the path integral dy bar exponential minus m over 2h bar integral du ui to uf y bar minus del u square plus omega square y bar. This will be given by some constant integral product over n greater than equal to 1 dy tilde n times exponential minus m by 2h bar sum over n lambda n plus omega square y tilde n square, where this is a constant to be fixed, because this path integral measure this C is independent of the paths, and we don't know a priori what value to choose, right? And we should choose this by demanding consistency with the result directly obtained from the Schrodinger theory, as I mentioned before. Now, these calculations, these integrals, there are infinite number of such integrals, and each, so sum over n, so you have in the exponent, so there are infinite number of decoupled integrals, each being Gaussian, and you can calculate that, and the result you can show to be given by this product n greater than 1, 2 pi h bar over m times lambda n plus omega square whole to the power half. Okay. Now, if you call this object to be f of omega, then for omega equal to 0, the fact you can take that factor out, c f0, and you take f0 out and multiply f0 with this, divide f0 with this, then you get n greater than or equal to 1 minus omega square over lambda n whole to the minus half. Basically, f of omega can be written as f0 times this factor, and then where lambda n, the expression for lambda n is this. When you weak rotate back, this uf minus ui becomes tf minus ti and an additional minus sign. So if you do the weak rotation in this final result, so inverse weak rotation will give you c times f0 product n greater than or equal to 1 minus omega square tf minus ti square divided by n square pi square whole to the minus half. Now you can use an identity, use this identity that sin x by x is equal to n greater than or equal to 1 minus x square by n square pi square. You can get it from, look at Arfken, for example. You can look at the book by Arfken. Therefore, this is same as c times f0 then square root omega tf minus ti divided by sine omega tf minus ti. This result becomes for free particle where omega goes to 0. So sine x by sine theta by theta, theta going to 0 is just 1. So it becomes c times f. So therefore, the result that we get for harmonic oscillator is, so finally the result that we get for harmonic oscillator, if I for harmonic oscillator is given by e to the power I by h bar is harmonic oscillator of x, okay, yeah, and times the path integral, and that path integral was c f0 times square root omega tf minus ti divided by sine omega tf minus ti. Now, if I do the same calculation for a free particle, then I would get e to the power I h bar s free particle and times c times f of 0. Now it is a straightforward job to calculate this s free particle, and it is given by, so you for free particle there is a linear motion, and you can find the classical solution x lower bar with the initial and final condition xf xi xi and xf, and then substitute it back into the free particle action and get the result, and the result is given by, you will find that result to be xf minus xi square divided by tf minus ti. Basically half m x dot square, x dot is the average value, um, half m x dot square times the time evolution. So x dot is the constant for free particles, so it's the average value xf minus xi by tf minus ti. Okay. Now we can calculate. Now we will we have to. The problem is to find this result in terms of my initial and final conditions, and because you see, so f0 is this product with omega equals 0. So that has infinite number of values in the product of infinite number of terms. And lambda n is this. So this is so let me, okay, to appreciate the problem, let me describe f0 more explicitly. So f of 0 is product over n greater than or equal to 1 square root of 2 pi h bar by m lambda n square root of 2 pi h bar by m lambda n being n square pi square and uf minus ui also. So uf minus ui, when we rotate it back, will give you minus times tf minus ti. Okay, so that is going to be product in greater than or equal to 1. Square root 2 pi h bar Tf minus Ti divided by n square I square. So of course it has Tf minus Ti. This object has Tf minus Ti. So since there are infinite number of terms, it has a large power Tf minus Ti to the power infinity. But at the same time, there is 1 over n square for each factor. So there is a damping factor. So this is something that is not easy to calculate. So what we are doing, so there can be a divergent piece if you regularize and all, depending on how you do that. And so that piece can be so the role of C is that when you multiply by C, then C can absorb the divergence, and it is C times F0 that can be meaningful. That is meaningful for the physical problem. That's what we should try to calculate. Since we don't know what C is just path independent, but it can depend on Tf, Ti, and so on, all the other parameters. So since we don't know what C ID to choose, we have to fix this. The goal is to fix C times F0, which is the only meaningful combination, physically meaningful combination, by calculating this directly using Schrodinger theory. So that is what I'm going to do now.